Quantum computers promise to solve problems that are impossible for today's supercomputers. They use qubits, which can exist in multiple states at once, exploring countless solutions simultaneously. But these machines are incredibly fragile. Tiny disturbances can ruin a calculation. Operating a quantum computer isn't like using a laptop, it's more like tuning a Swiss watch during an earthquake. Historically, you needed a team of PhDs to keep one running, constantly tweaking and troubleshooting. This complexity creates a massive barrier for businesses. If you need a quantum physicist just to turn it on, how can anyone use it? The focus has been on building the engine, but not the controls that make it usable. Without a way to manage this complexity, quantum computing remains impractical outside research labs. Companies can't build business models around technology that requires constant expert maintenance. For quantum computing to move from the lab to the boardroom, something fundamental must change. The real challenge isn't just better hardware. It's building software that makes quantum computers usable. The solution lies in the software that sits on top of the hardware. Classical computers became easy to use thanks to layers of software abstraction. You don't need to understand transistors to send an email. An operating system handles the complexity. Quantum computers need the same, software that acts as a translator between users and the hardware. Quantum infrastructure software is emerging as the operating system for quantum machines. It automates calibration, manages errors, and translates high-level problems into quantum instructions. This software virtualizes the quantum computer, making the hardware invisible to the user. At the top layer, you can define your problem in a familiar language like Python. The software designs the quantum circuit, runs it, and returns a classical answer, hiding the quantum complexity. This lets users focus on their problem, not the physics. The first challenge is making quantum hardware work reliably. Quantum machines are sensitive and need constant recalibration, a job once done manually by experts. Q-CTRL's Boulder Opal automates this process, acting as a quantum auto-booter. It uses AI and physics models to learn each processor's quirks, running diagnostics and tuning the hardware automatically. This isn't a one-time setup. Boulder Opal continuously monitors and recalibrates the system. The result? No need for a human operator to babysit the machine. Quantum computers can now be managed like standard servers, reducing costs and complexity. Boulder Opal provides a stable hardware foundation, ready for any task. This reliability is the first step in making quantum computers practical tools. Even with stable hardware, quantum computations are prone to errors. Q-CTRL's Fire Opal acts as a smart compiler, optimizing algorithms for the specific device. It restructures circuits to minimize errors and uses built-in error suppression during execution. This can boost performance by thousands of times, turning failed experiments into successful computations. Developers no longer need to be experts in error correction. Fire Opal handles it all. Just submit your algorithm. Fire Opal optimizes and executes it for you. It virtualizes the quantum processor, presenting a more powerful, reliable machine to the user. This abstraction lets developers focus on logic, not hardware quirks. Fire Opal bridges the gap between quantum theory and real-world results. It makes quantum computing accessible and effective for practical use. The goal is to make quantum computing accessible to anyone, not just quantum experts. The final software layer combines Boulder Opal and Fire Opal with high-level tools. Now a financial analyst can define a problem in Python, and the software handles everything else. It translates, optimizes, and executes the problem, delivering a classical answer, no quantum knowledge required. This hides all complexity behind a simple interface, letting businesses use quantum power without hiring physicists. Quantum resources can be integrated into existing workflows as just another tool. By automating hardware and workload management, these tools unlock quantum computing's commercial potential. This software bridge finally brings quantum power to real-world industries, driving the next wave of innovation.